All right, so in these next couple of examples, we're still going to be looking at this idea of we're given some really big, nasty statement. We want to try to decompose this thing into a bunch of little parts and then ultimately look at the truth table. For this particular example, we're actually going to see something really weird happen in the truth table, and that's going to guide our next little bit of discussion. So in this case, we're going to be looking at this big statement which reads, whenever Apple updates iTunes, it either announces a new iPhone or it does not announce a new iPhone. So right from the get-go, just kind of as an English statement, it does sound a little bit weird, and that's going to kind of lead into some really weird things that are actually happening in this example. So what I want to do first is I actually want to try to attack this thing by writing it down in symbolic form. So hopefully when you look at this thing, you can kind of see a classic conditional statement going around. It is triggered by this word whenever, which I'm going to view as this if. So I'm going to have this statement that Apple is going to do something and then it's going to cause some other stuff to occur. So in this case, it's whenever Apple updates iTunes, then, or in this case, some stuff's going to happen afterwards. What's going to happen afterwards is it's going to either announce a new iPhone or it's not going to announce a new iPhone, which sounds kind of weird. It's this idea that those two things do seem to play off each other relatively nicely. What I want to do is I want to give these things some kind of symbolic names. I'm going to call this hypothesis just my P because I'm lazy and not overly creative when it comes to labeling these things. The next little part, you're going to see that my conclusion is actually separated by an or, so there's going to be this little V making an appearance. And then I'm going to have two different things. But if you look at this, those two different things are actually the same statement. One just happens to be the negation of it. So there is this little word not floating around. So I'm going to have this Q or not Q. So in this case, there's going to be that Q statement, and then there's that not, which is going to bring about that negation, and then it's the exact same statement afterwards. So the overall statement for this thing is going to look like P, and then I'm going to have my conditional arrow, which is going to point to Q or not Q. So that's what my statement's going to look like, kind of embedded into this symbolic language. I have these kind of my hypothesis, this P, I have my conditional arrow, I have this or, and then I have these negations around these Q's as well. What I want to do is I want to try to build a truth table for this thing, and you're going to see that I have really just two little statements going around. There's a P and a Q. So when it comes to actually identifying the rows for this thing, I'm actually only going to have 4 rows. I don't actually need 8 because I have just P's and Q's. I don't have an R or some other statement floating around. So let's go ahead and see if we can build this thing. I'm going to have a P, I'm going to have a Q, and then I'm going to try to build up all the little pieces to actually get to that final statement. What I'm going to want to do is I'm going to want to see a not Q column float around. I'm going to want to see a Q or not Q, and then the very last part of that thing is going to be my big overall statement. I'm going to have a P implies Q or not Q. Okay, so let's think about all the possible combinations that can occur. Well, I can have a true and a true for both P and Q. I can have a true and a false. Otherwise, I can have a false and a true and a false and a false. So those are the 4 possibilities for my P's and Q's. They're kind of truthfulnesses in this case. What I want to do is I want to negate my Q, which is just going to change all of these to a false, a true, a false, and a true. Now I'm going to look at Q or not Q, and in this case what's going to happen is that as long as one of these two things picks up a true, that overall statement of or is going to pick out a true. So you can see in this case I have a T, a T, a T, and a T. So what's going to happen is that that whole column is going to turn into a T, a T, a T, and a T, which is already kind of indicating some really weird things that are going to occur in this case. I do have a column of all T's. What also I'm going to have another column of all T's over here, because you can see that I'm going to have this conditional statement, which is going to say, hey, I have my hypothesis P over here. I'm also satisfying my conclusion. Both of those are trues, so my conditional is going to be true as well. Same thing for that second row, a T and a T is going to make a T. And then the last two, I really don't care what my conclusion is because I know that I'm failing my hypothesis, so my overall conditional is still going to be true. So I'm going to have a T and a T. So what's happening in this case is you can see that no matter what the truth values of P or Q happen to be, my overall statement's always going to be true. In every single version, I'm going to pick up a T, a T, a T, and a T. So that's actually a really special thing that's going to happen in this world. This is going to be referred to as a tautology, which is going to be some statement that is always true. And we can look at another one of these things. In this case, all I've done is I've actually just identified just the overall statement. This is just written in this kind of symbolic logic. It doesn't have a sentence connected to it, but you can always create one on your own. And that's actually something I would recommend you doing. Anytime you're given just some kind of guts looking like this, it always helps to just create some kind of hokey looking equation for this thing, or hokey statement for this thing. If you double back to some of those very first ones, we had these statements about Jeff owning a toy store, Jeff liking board games. You can always just think about these statements with those kind of cheap little statements kind of embedded into it. So in this case, if you tried to think about P being the statement, Jeff owns a toy store, and Q being the statement, Jeff likes board games, well, that statement up above would say, if Jeff owns a toy store, then Jeff likes board games, or Jeff does not like board games. So the idea is that if you want to think about what's going on in this case, you want to think about, is there going to ever be a situation that that statement is false? And in this case, the easiest way to see that is just by creating a little truth table. You can kind of try to logically reason it out in your head, but you can also just sketch out a truth table to know for sure that this thing is in fact going to be a tautology. And if we go ahead and create this thing, I'm going to have a column for P, I'm going to have a column for Q, I'm going to go ahead and create my P implies Q column, I'm going to create a not Q, and then at the end of the day I'm going to have a P implies Q or a not Q. And if I go ahead and create this thing, I'm hoping to see a whole bunch of T's come up on that very far right column. And that's exactly what I'm going to have in this case. So let's go ahead and see if we can actually double that up again. So again, running through all of the possibilities for P and Q, I'm going to have a T and a T, a T and an F and a T and an F and an F. So I want to think about what is the truthfulness of P implies Q. In this case, it's a conditional. The only time I'm going to kick out a false in that case is if I satisfy my hypothesis but fail my conclusion, which is going to be that second one. And in all other cases, I'm going to kick out trues. The negation of Q is just going to be the opposite truth value of these things. So I'm going to have a false, a true, a false, and a true. And then I'm going to go through and try to think about the statement of this one or this one. So I'm going to look at this column right here, compare it to this column right there. And if I happen to have at least one T in those two things, I know that the overall statement's going to be true. And that's exactly what's happening. I'm going to have a T here, which is going to say that my overall statement's true. In this case, I have a T right there, which says I have a true. Over here, I still have a T, so I'm going to pick up a T there. In this last case, I actually have two T's. In this case, it's just the classic OR. It's not this XOR, this exclusive OR. So having two T's is totally fine. And in this case, I'm still going to pick up a T. So in this case, you still have the situation that all four versions of this are still going to kick out a true. So no matter what the truthfulness of P or Q happen to be, this overall statement is always going to be true. So this is what we're going to refer to as a tautology. And that's the official statement or the definition down below. It's this idea that a statement that is always true is going to be referred to as a tautology. The exact opposite, a statement that is always false, is going to be referred to as a contradiction. And then there's going to be this kind of what happens in the middle. There are some statements, we've seen some already, that happen to be true sometimes, false some other times. There's kind of a weird mixing. What we're going to refer to those things is they're going to be referred to as contingent. They depend on particular truthfulnesses of certain statements to determine whether or not the overall statement is true or false. So in this case, you can see a little bit of terminology. What we're going to do in the next couple of videos is just continue to look at whether or not certain statements are tautologies, contradictions, or if they happen to be contingent. But for now, it's kind of a nice just setting the stage for seeing these types of kind of weird definitions come into play. Also, the idea that there are statements that always happen to be true is kind of a weird thing. But if you think about them as kind of the English version of the statement, it also makes sense. This idea that if Jeff owns a toy store, then Jeff likes board games, or Jeff does not like board games. If you kind of reason that out, you see that, oh yeah, no matter what, that's always going to be a true statement. What's nice about the truth table is that it allows us to really quickly and efficiently determine if that statement is a tautology. Sometimes wrapping your head around the actual English version of all those things can be somewhat challenging, but if you actually create a little table out of it, it's really easy to say, hey, this statement's always true no matter what. Or in some other cases, this statement is always false. And you can kind of go from there.